Good afternoon, student. It's the 12th lecture of Module 1 related to number theory. Especially in this lecture, we learned a very important theorem relating to greatest common divisor, and it's also very important for your examination. So here we start to define the theorem and the corresponding proof. So first we move to the theorem. What says this theorem? Theorem says if a and b are integers, both not zero. It's very important, both not zero. That means it should not be happen that you consider two different integer and these two different integers should be zero. That should be a same case. So you should always consider the non-zero integer, at least one non-zero integer. Then there exists integer u and v such that the GCD u a comma b should be written as AU plus BV. The GCD a comma b should be written as AU plus BV. In the previous theorem, when we discussed the division algorithm, in that case we mentioned when we divide a by b, or say a by b, then a should be written as bq plus r, where q and r both are the unique. That should not be defined in the other way. But here we should not mention the term u and v are unique. It may be, and that means you can write this one u and v should should not define that u and v should be unique. So for that reason, here we construct, when we start to prove, first you have to construct the set. Before we move to the proof, first thing you have to recognize, if you defined a number is a greatest common divisor, what should be the goal for the procedure of proving? First, you have to consider a number which should be the common divisor. Okay, and after construction this common divisor, you have to prove that this common divisor is the greatest common divisor. That means if we consider another common divisor of the given number, this common divisor should divide the greatest common divisor. Exactly for that reason, here we construct the procedure of the proof is, first we defined the common divisor, next we construct this common divisor should be the greatest common divisor. That is the procedure of proof. Exactly, we start the same procedure of proof. And another thing is very important, we have already learned in the last lecture, GCD should not be a negative number. Okay, it should be a non-negative number. That means first we construct a set which should be the collection of non-negative integer. Okay, so we start our proof according to the knowledge of, first we construct a non-empty set which is a non-negative integer set. Next we prove that there is a common element which divides both the element a and b, that should be the common divisor. Next we prove that when we construct this common divisor in such a way that the other common divisor, if we consider the other common divisor, this other common divisor should divide the greatest, should be a divisor of the greatest common divisor. So we start our construction of the set. That is the first line. Let s equals to ax plus by, where x comma y belongs to z, and ax plus by greater than 0. That is the procedure of construction of the subset S. Because when we consider ax plus by which is greater than 0, that means it's represent the set of non-negative integer. The question arises in your mind is should be that why it is called the non-negative, because a and b are two integer, and x and y both are the integer. Therefore the linear combination of ax plus by should be a integer. So the set S should be a set of integer. First we construct that this set must have a element, because if the set is a empty set, nothing to work. exactly for that reason, first to check that is this set is a non-empty set or not. So exactly for that reason, here we first construct this set represent a non-empty set. Since at least one of A and B are non-zero, it is given that at least one of A and B are non-zero. Okay, at least one of A and B is non-zero. That means they should not be zero. That means we can write, if we, without loss of generality, we can easily write A not equals to zero. Since A not equals to zero, that means its modulus value should be greater than zero. It's basic. If we consider A equals to minus 5, mod 5 is mod of minus 5 should be 5. So here it is the way of construction of the element mod A, that is A into x plus B into 0 is an element of S. That should be an element of S because mod A is a negative integer, and this number can be written in that form ax plus B into 0. Because if a is itself is a negative number, in that case we should choose x equals to minus 1. If x is a if x is a so if we consider a itself is a negative number, then we just consider x equals to minus 1. In that case, its more value becomes minus 1 into the value of a is minus 5, that becomes plus 5, and that should be equals to the absolute value of mod 5. Exactly for that reason, here we consider the way of construction of mod A is in that form, and which is similar to the element of this set ax plus by. For that reason, we say that A, at least mod A should be belongs to the set. That means S is a non-empty. S is a non-empty subset. So, since it's a non-empty subset, therefore, according to well ordering principle, we say that this set must have a least element. Okay, this set must have a least element. That means the set S must have a least element. According to well ordering principle, it says that if we consider all the integer set or all the subset of the integer set, they must have a least element. If we consider S be this set, and which is we have already proved that this set is a non-empty set, therefore we should say S, according to well ordering principle, S must have a least element, content at least element, and here we mention this least element is by D. Just to consider this least element is D. Since D is your least element, so D can be written as AU plus BV, because every element of this set should be written as AX plus BY. Here we consider that the value of X is U and the value of Y is V. Okay, for some integer U and V. By the division algorithm, we have already learned by the division algorithm, if we divide A by D, this should be written as dq plus r. That is the division algorithm basic idea, where n, r, q and r are the integer, and the value of r should be lies between 0 to d. The question is that when we consider the division algorithm, here we consider mod d, but still here we not consider the mod d, because d itself is a non-negative integer, so we should not mention the mod value of this. Okay, so exactly for that reason, here we consider the value of d should lies between 0 to d. Since the value of d lies between 0 to d, the question is that what should be the value of r? The value of r, what should be the value of r? For that reason, here we construct another concept for you. Concept is exactly, if we consider r is a non-zero quantity, then r should be written as a minus of dq. Okay, and r should not be a negative number. So if we put this value of d here, the result becomes a minus aq plus bv. That is, if we calculate this one, a into 1 minus of u and b into minus b into q, which is exactly in the form of the element of the set ax plus by. exactly in the form ax plus by. Since it's a form of ax plus by, that means r should be belongs to s. Okay, because r itself is a negative non-negative number, so it's proved that the r is greater than 0 and r belongs to s. Since we consider d is the least element, it's very important line for you. Since we consider d is the least element, d is your least element. Since d is the least element, in that case, if r belongs to d, r belongs to d. If d is your least element or r belongs to d, it's also represent that r is lesser than d. It's also represent that r is lesser than d, which is a contradiction that d is the least element, but still we consider d is the least element. So the only case arises r equals to 0, because it should not be happen. Okay, so if r is 0, it's represent that the number d should be a divisor of a, because r is 0. Because r is 0, therefore a should be written as dq. That means it's represent that d should divide a with the quotient q. So a equals to dq. In the similar concept, we can also say that b equals to dq. Okay, with a similar concept we can say b equals to dq. Since b equals to dq, a equals to dq, it's represent that d is a divisor of a as well as d is a divisor of b. That means d is a common divisor. D is a common divisor na. D is a common divisor of A and B, because D divides A, D divides B. Therefore, D should be the common divisor of A and B. Since D is a common divisor of A and B, we have already mentioned the procedure of proof of this theorem is that first we consider the greatest common divisor should be a common divisor. Next, we prove that if we consider any common divisor, this common divisor should be a divisor of the greatest common divisor. In that case, we say that the number should be a greatest common divisor. So the last part of the proof should be that you have to prove that your least element of the set D should be a greatest common divisor of A and B. Exactly for that reason, here we consider C is a common divisor of A and B. Just we consider C is a common divisor of A and B. Since C divides A, C divides B, according to a theorem we have already learned in the previous lecture, if C is a divisor of A and C is a divisor of B, then C should be a divisor of any linear combination of A and B. Therefore, C should be a divisor of AU plus BB, which is a linear combination of A and B. So this represent is nothing but D. Since this represent is nothing but D, which represent that if we consider C is a divisor of C is a common divisor of A and B, then C should divides D, which is the greatest common divisor. So C should divides D, and this proof that D is the greatest common divisor. And that's all for the proof is that because when we start our proof, we just consider that the element comes exactly from this set, exactly from this set, exactly from this particular set. That means this set should be represented by ax plus by. Okay, so the way of representation ax plus by may be different, but the least element is unique, so the greatest common element is unique, but the combination of the element a and b should not be the unique case. Okay, that's all for this particular lecture, and happy learning. Thank you. Thank you for listening.